Hear me, just to check.
I can hear you.
Yes, we can hear you.
Okay, great. We will start for a minute.
But there are some other voices behind you, maybe. It's quite a loud place. Okay.
Okay, we can start.
We break for a few minutes at 11. So I want to get set up on the
Okay, our presenter, Professor Liam, needs a few minutes, so please, we can wait for him. Okay, now is everything okay? Hello to everyone. Welcome to our webinar, Microplastic Chronicles, Stories from the Cutting Edge of Research. I am Natasha Stojic, and I'm thrilled to be your host today. We are gathered here in this virtual space to explore one of the most pressing environmental issues of our time, and that is microplastics. As we all know, microplastics have infiltrated every corner of our planet, from the depths of the oceans to the peaks of our mountains, and even we have microplastic in the air we breathe. So the impact of these tiny particles on ecosystems, wildlife, and human health is the subject of ongoing and critical research. Today, we are honored to have six distinguished presenters who are at the forefront of this vital field. They will share their latest findings, insights, and stories from their cutting-edge research, offering us a comprehensive understanding of the challenges and potential solutions associated with microplastics. But before we dive into Microplastic Chronicles, I would like to give the floor to Professor Dr. Andrejević Panić, Vice Rector for Science and International Cooperation at Educons University, to present shortly our university. Professor Panić, please, the floor is yours.
Thank you so much, Natasha. Good day and welcome, everybody. I am certainly honored and proud to be here with you today, and for this opportunity for Natasha to present or to say something about educons as well. I'm also very aware of the importance of sustainable economics and economic development, and also green agenda, European agenda for our recovery for our industries. And so the 4 S's in terms of sustainability, such as safety, security, sustainability, and social responsibility, are, in my opinion, the imperative of today's world. Concerning my position, currently I am Vice Rector for Science and International Cooperation at Educons University. I've been here for 3 years on this position, but at Educons I was since I started. So I am really thrilled to welcome you on behalf of Educons Rectorate's office and our rector, Professor Dr Aleksandra. Educons is started to be an integrated concept in 2008. Since then, he developed an science infrastructure, but also people. So for now, it is very dedicated to develop young people, especially in life sciences, but also sustainable economics with an accent on circular economics. Not just the international project, but also very important and crucial for Educons' social responsibility and its engaging work. For now, Educons has 7 study program on all three levels of study, on all 3 levels of degrees. So it has a study program or the Faculty of Environmental Protection, also the Faculty for Ecological Agriculture, the Faculty for Teaching, the Faculty of Business Economics. Hello, Professor. The Faculty for Digital Production, Informational Technology as well, and Social Security, Security Studies, or moreover, Corporate Security. For now, this concept has been really creating one synergy, and all of our researchers are working together, forming the research teams among our staff. And I'm very happy that now during this GREENLand project, I can really lead this research team and engage myself in all project activities for our university. Our university is middle-sized, so therefore projects like GREENLand are extremely important for its development. And I'm looking forward to let's say, work with you or to engage in part of your work for capacity building from Educons University and International Relation Office, also project office that we just recently established. So I'm wishing you all pleasant workshops and also days and productive presentations. So thank you once again, Natasha, and I'll be here open to all of your questions. Thank you.
Thank you so much, Andrea. So now we can start with official part of this webinar. Our first presenter, according to the agenda, is Professor Stefan Krause, but we will wait for him to join us maybe later. And please, Professor Agnieszka Dąbrowska, can you hear us?
Yes, I can hear you. I have some problems with my connection, so I'm very sorry, but I just try to... can you hear me?
Yes, we hear you. Professor Agnieszka Dąbrowska is an assistant professor at the University of Warsaw. She carries out interdisciplinary research on the use of physicochemical methods in ocean and environmental science. She has been involved in the nanomaterials design and nano-composite studies. Her scientific activity at the Laboratory of Spectroscopy and Intermolecular Interreactions currently focuses on various aspects of the marine nano and microplastics, 2D materials, ecotoxicology, and plastisphere. She was a member of the scientific polar expedition of Polish Academy of Science in 2017 and 2023. From 2018, she is an honored ambassador of Poland at European Maritime Day. Professor Dąbrowska will tackle the challenges in characterization of nano and microplastics, state-of-the-art and selected examples. This session will highlight the latest advancement in identifying and characterizing these particles, crucial for understanding their environmental impact. So, Professor Agnieszka, please share your presentation. Yes, we see your presentation. The floor is yours.
Okay, thank you very much for your kind introduction. And first of all, thank you for the invitation to be here. I'm really honored and pleased. Since I have only 10 minutes, if I'm right, I will be very brief. So please treat it as the starting point for the further conversation or discussion. You will have my contact because that will be really brief overview. So as introduced, I mainly the spectroscopist, and my point of view is related to physics and chemistry, and the so-called drop lab, which is the implementation of the following techniques, which is the mainly infrared and Raman spectroscopy to resolve the problems related to environmental and ocean study. And of course, microplastic, which is the high topic. I had the pleasure to work in the domain of microplastics for more than 12 years now, being at each stage from sampling with identification, then possible consequences of the plastic presence in the environment. But today I will focus on this area that we are specialized in as our laboratory, which is mainly the spectroscopy with several configuration and possible device. The key message to take home, actually, that I will start with, and I will let you to discuss it more, maybe, is that we point on structure. So we say that the crucial to understand the toxic effect of microplastic and understand the effect and behavior will be the understanding of the interface, which is basically the starting point. And to that, of course, to understand as much as possible the material side of microplastic, we use the spectral techniques. So starting shortly with identification modeling, we all know that using both infrared and Raman spectroscopy, we can collect signal and identify the type of polymer we have in microplastic. However, we would like to go beyond that, so not only creating a robust databases of different kind of debris, but also trying to use the signal that is not related to type of polymer, but to added compounds, to the possible leakage, to the weathering mechanisms, to aging, and so on. Because that would be crucial to understand whether we have plasticizers and to what extent they can go to the environment from our type of plastic. We can also use the so-called background signal to determine whether we have the plastic from the local source or whether this is a plastic type. So to distinguish the debris that is locally from the shore and the one that's coming from high seas. And this is one of our recent paper. The second thing is a so-called quantification of the spectra. So instead of only saying what type of microplastic and material we have, try to understand how whether it is. You probably know the carbonyl index, so the amount of oxygen group we may determine as one of the features of aging of microplastic, but we also can have various other types of signal band that we use for modeling. And this is what am I doing. So for different types of spectra, I'm trying to numerically propose the profile to do the deconvolution and to understand to what extent different types of bands are related to different chemistry on the surface. This is relevant for several reasons, but one of that is a practical one, understanding better the aging of polypropylene in that case, and having a lot of research on ghost netting and fibers that are from the environment. We were able to propose the aging pattern, the structure modification on the interface, and we were able to recreate them in the new material, composing the pristine polypropylene and the polypropylene from ghost netting, so from the fishing jar that was lost or abandoned at sea. As you probably know, the huge problem with bycatch, with entanglement of biota, and presence, of course, of possible source of microplastic, because the weathering fishing gyre creates a lot of fibers during its aging. This is recycling, but also upcycling is possible. Another domain of my interest is primary microplastic, and this is somehow starting with the same hypothesis that the interface is crucial. So the smaller is the debris, the larger is the surface to volume ratio, isn't it? So starting with that, microplastic can possibly be already bioavailable for biota, being smaller and also have a larger surface to interact. So that's why we struggle with those that are in cosmetics. I don't know if you are familiar with a small curiosity with glitters in fish baits. So we have a fishing ground bait that is put directly to the fresh water, and it contains a lot of glitter. So we study the glitter impact also on soil environments. Second chapter related to that would be more about aging, so quantification of aging and structure modeling. And also, to cut a very long story short, we would like to put the morphology into numbers. So instead of showing you the picture and saying this one on the left is more rough, then this one on the right, and so on, we would like someone to parameterize it. So to create numbers that would be easily transferable and correlated with the presence of a certain biofilm. Of course, creating scanning electron microscopy picture is also a challenge. We were able in 2019 to propose how to do it for microplastic without any additional coating. Because if the surface is crucial, if the morphology pattern is crucial, then any coating that is needed for scanning electron microscopy will destroy this picture. So you may find in our papers how to do it at the low angle without any coating. Additional several parameters to understanding, to put into the numbers, and also to recreate a 3D morphology. And once again, why is it important? A bit like with quantification of the spectra, there is a practical issue hint with that, and it's related to the biota. So we have a plastisphere biofilm, so the type of bacteria related to the surface, and we are looking for the morphological correlations between exactly what type of bacteria we have and what is the aging of the plastic. And this is much more susceptible parameter than spectroscopy, because as you can see here, polypropylene aged for several months in natural environment of the lake does not show any difference. It's still polypropylene. It's not surprising, I guess, to us, but it shows a lot of cracks and a lot of at the nanoscale changes in the morphology, and so were the changes of biofilm on the surface. Spectroscopy is also useful to understand how animals impact on the material. So what are the natural decomposition patterns? In that case, that was the degradation of macromolecules induced by moles, so by Plodia interpunctella. And finally, to wrap it all up, this connection between morphology, material science, and toxical issues. This is my key topic, I would say. So I'm a sort of a bridge trying, or a dictionary, if you like to say, to putting on one table a physics, chemists, and biologists and trying to make them understand each other. Here you have our tracking of the passing of microplastic in a web, food web in a trophic chain, and at each step of this passage, the material science was done, so we were able to detect whether microplastic itself is hampered by an animal, whether it changes its morphology, whether the structure is different, and what's the consequence possibly on a toxic response. We also detected that fragmentation occurs on one side due to aging, but on the other side, which is very tricky, is the agglomeration. So if the particles are really the small one, the agglomeration will tend to assume that they are a bit bigger. And of course, the leakage and the huge problem of fluorescent dye. From one point of view, fluorescent dye will create such a beautiful picture showing you where the microplastic is placed within the animal or its tissue. But on the other hand, fluorescent dyes are toxic themselves. So somehow to entangle those two types of effect is also crucial. The same on a long distance. Here you also on the mapping can see a beautiful agglomeration of nanoparticles. So after the first passage in a food web, they are not longer nanoplastic, they are microplastic in a way. So this is a short summary of microplastic problem in general from my perspective that would be put up to the three key question where it is. So all monitoring, tracking in the environment, what type of it is, so the identification, but going a bit beyond that, understanding identification also by quantification of the aging, and why is it important, why we should bother, so the problem of the toxicity. A huge list of people I had the pleasure to collaborate with, placing researchers, but also placing my beloved students in here and people that are responsible for whole lab and infrastructure we have. end with that perfectly in 10 minutes. Thank you for your attention, and I hope that it was not too fast, and invite you to any contact and future discussion, leaving you also with this one step forward to additional questions that we're taking out from this presentation. Thank you.
Thank you very much, Professor Dąbrowska, for your interesting presentation. I hope that you will have some questions from our audience, but we will have the questions at the end of all presentation, at the end of this webinar. So please take a note for these questions. Our second presenter is Professor Dr. Aleksandra Tubić. Dr. Aleksandra Tubić is a full professor at the University of Novi Sad since 2023. She specializes in environmental protection, focusing on microplastic behavior, remediation technologies, and environmental engineering. Leading the Serbian team in 2 Horizon Europe projects and serving as a vice chair of the Coast Action Priority, she actively contributes to the EWA Groundwater Management Group. With 64 papers in STI journals, she fosters knowledge exchange between academia, industry, and policymakers in environmental protection. Professor Tubić will present extraction methods of microplastics from complex environmental matrices. This talk will focus on innovative techniques for isolating microplastics from various environmental samples, a key step in accurately assessing their presence and effects. So please, Professor Tubić, share your presentation, and you have 10-15 minutes.
Thank you, Natasha. Can you see my presentation?
Yes.
Okay, so I will not see you then, but it's important that you. Okay, so wait. I had some message here. Is it in presenter mode?
No.
No.
And now? Now it should be.
No, it is still not.
Wait, I will then stop sharing and then do it again.
Okay.
Okay. Can you see it now?
It is still not in presenting mode, but it is okay, Aleksandra.
Yeah, it's okay to to lose any more time. So thank you, Natasha, and the whole team of Educons University for inviting me to give this lecture. Since it is a very short time, I will go ahead with my topics with no further ado. So today I decided to share with you our findings through the literature review, which we made through Cost Action Priority, together with our action chair, Stefania Federici, and her team, and also our working group, 2 leaders, Liam Morrison and Zaida Ademovic. So we did a very comprehensive review of all the available literature in that time related to the extraction method. Since we recognize that the extraction method is really demanding step in the preparation of the complex environmental matrices, and since I don't have too much time, I will focus just on one type of environmental matrices, and this is soils and sediments. Since I know that the team from the Educons is much focused on the soil analysis and monitoring. So if you are a little bit in the field of microplastics and environmental protection, this kind of schemes can be very familiar for you. So usually what we do with the soils is that we are first dried under the room temperature or a little bit higher than the room temperature. After that, usually we go with digestion.
Sorry, Aleksandra.
Yes.
You're on the first slide still.
Okay. I don't know why is that.
You must manual, yes. Thank you.
And now?
Yes, it's okay.
Okay, sorry. So the second step is the extraction, which we will focus today on, and then usually we use some kind of filtration, and we get as a result our microplastics particles in some kind of filter, which we use further for the analysis with the several techniques. So. Focusing on extraction methods, I will present you today the usually used extraction methods by the researchers worldwide, and the first and the most used is density separation using hypersaline solutions, then the electration, pressurized fluid extraction, magnetic separation, electrostatic separation, and also oil extraction. And yes, I have to say here, because I don't have time to go through all the advantages, disadvantages, and protocols in this presentation, I chose, since all these methods are used, they have their advantages. So I chose today just to show you what are the limitations of these methods and for which kind of soils they can be used. So the density separation using hypersaline solutions are based on differences in density of the polymers and flotation solutions. It is widely used because it is a simple method, and it is showing that it is very effective. And usually the researchers use these salts they already have in their laboratories, like sodium chloride or zinc chloride or some other salts. However, this method has some limitations, like that organic matter and wetting agents can heavily impact the extraction efficiency. So usually we have to remove it through some previous step of digestion. Also, there is a concern about the usage of some toxic salts as a flotation solution. So it can be dangerous to the health of the analyst. Repeatability, reproducibility, and the representatives can also pose the issue in this method. It is not suitable for all the microplastic dimensions, and overlapping densities are usual among the polymers, so it is not efficient enough for distinguished different polymers. The other one is electration. It uses the steam of gas or liquid to separate particles depending on their size, shape, and density, and usually in the direction or opposite of direction of sedimentation. This method is very suitable for the sandy sediments, but it has a little bit poorer efficiency for the sediments or soils which are rich in organic matter, which can agglomerate or react with the plastic particles. The third one is pressurized fluid extraction. It is a very promising extraction method. Uses organic solvents to extract semi-solid materials with high pressure and elevated temperatures. It is usually automated method, enables matrix removal and microplastics enrichment to the completed in single fully automated stage. However, also has some drawbacks. That is limited in the ability of to offer size information. It is destructive, leading to the morphological changes in the microplastics. It is not very good in providing information on microplastics which are bigger than 30 micrometers. Residues from materials containing various types of microplastics can contribute to acquirement of a suitable, for example, FTIRs factor, and usually some toxic fluorinated solvents are used in the protocols we found, and that can be concerned for the human health. Magnetic separation is a new technique very in the beginning of investigation. So usually synthesized hydrophobic iron nanoparticles are used to bond the plastic and facilitate magnetic recovery. It is more effective in removing small microplastics. Recovery rate for sediments is poor because soil particles prevent nanoparticles from colloids with microplastics due to the relatively low surface area to volume ratio. It is lipophilic chemicals or biota will limit the use of these methods, and the technology may be more suitable for, let's say, post-density separation of the or digestion stages and for drinking water treatment. But we could find also some information in the literature using this method for the soils. Electrostatic separation also is not very widely used, but we have to mention it here. It is based on varied electrical conductivity of the sample particles, with mineral particulates in soil and sand being more conductive than polymers in general. The sample drying process is tedious. Humidity can have adverse effect. Tiny particles can and agglomerates also can have adverse effect for this method. Electrostatic separation of microplastics need further treatment, such as density separation or digestion, but still can have their they found their place in some research papers. Mineral composition has a significant also influence, and also one of the drawbacks is that sediment loss. And in the end, it's the last one I will show. It's oil extraction protocols, where we use the oils to distinguish extract the microplastic particles from the samples. It is determined that it can increase the recovery rates. However, also there are some limitations, like that microplastics are not transferred fully to the oil phase. They can remain intact in the filters or gas surfaces while transferring we can underestimate the efficiency of the extraction. Also, due to the use of reagent alcohol, microplastics have high static electricity during examinations, and shaking the sediment with water and oil often results in the formation of an emulsion, which is very hard to work with further. So in the end, all these methods are can be found in the literature. The researchers are using it for various for the same matrix, but for the various purposes. So in the beginning, we have to know what samples we plan to analyze, which findings we expect from our analysis, how are microplastics sorted from the other organic content, what are the characteristics of the performance method, what are the limitations of the method we use, and then decide which methods we can apply and which is the most suitable for our purpose. We also have to know which analytical method we will use after the preparation of the samples, and also it will affect what we will use for the extraction method. However, there is a positive trend in recent years indicating that greater understanding of fundamental relevance, so the matrix processing in the pursuit of high quality analytical results and also valid conclusions. And with this picture of my research group, and I thank you so much for your attention.
Thank you very much, Professor Tubić, for your great presentation. And as I said at the beginning, we will have a chance to ask you something about your presentation, about your results at the end of this session. This webinar is organized within a GREENLand project, which is a Horizon Twinning project, and we are very happy because on this project, where the University of Educons is leader, we have two partners from Ireland, University of Galway from Ireland, and Alfred Wegener Institute from Germany. And today our partners are here with us in Novi Sad. Now our fourth presenter will be Dr. Sebastian Primpke. He is a researcher in the Department Shelf Sea Systems Ecology of the Alfred Wegener Institute. And he is an expert in analytical and physical chemistry and holds a doctorate and diploma degree in chemistry. His doctoral studies focused on polymer science before he moved into his current position in the microbial ecology, Microplastic Research Group. Here, he focused on the analysis of microplastics in various environmental compartments for microplastics, ranging from aqueous samples, including melted ice and snow, over solid matrices to biota. In this scope, he developed analytical methods using FTR and Raman spectroscopy with the aim of an automated analysis of the results. He is part of the AMAP expert group for marine litter and member of different working groups of the German Institute for Standardization and the International Organization for Standardization. Dr. Primpke will discuss the significant analytical challenges posed by microplastics and the methodologies developed to address them. So please, Sebastian, share your presentation and the floor is yours.
Yes, thank you for a kind introduction. I hope you hear me well. And now I hope you see my presentation. Thank you, Natasha, for this kind introduction and welcome you all. My topic today is microplastics in the environment, small particles, big analytical issue. We had already two nice presentations in front of my presentation, introducing you a little bit to the analysis of microplastics, but also sample preparation. Those will also be a little bit covered here. And yeah, how it comes that we work on microplastics, because we are normally working on Helgoland, and no, it's an island in the North Sea. How does it come? So we have more or less a rocky shore, which is really nice, that we are famous for bird watching and tourism. But we also, due to this rocky shore, have the Biologische Anstalt Helgoland, which is nowadays part of the RV. And you might see these nice birds here. They also tend to put in plastics into their nets, so this is a known issue to us. And here we set up, since 2013, a dedicated laboratory for plastics analysis, but also work on microplastics. We currently using several FTR microscopes, one spectrometer, Raman microscope, and a nano FTR, and analyzing all kinds of samples from treated wastewaters, drinking water, river sediments, river waters, but also samples from really remote areas like Antarctica, Antarctica, ranging from ice, but also snow or water samples and sediment samples. Why we spend so much time on analyzing all the samples? On the one hand, we are requested it from the different monitoring agencies to identify small microplastics, but also, as you heard in the first presentation today, it's not only type, it is the plasticizers, leach, additives, and so on. And we should, for risk assessment, provide all information, especially if you see particle shape can have an issue. It influences the residue time, the polymer type, as it can reach different types of chemicals, including monomer units, but also then the size determines the uptake into an organism or even translocation into cells, but also what is can be different is how this digestive organs are blocked. For example, large microplastics are a big issue for turtles, which we would not consider any issue of health for anyone else, but as it's blocking the digestive system, it has a big impact and a big effect. And as you see here, we have different compartments. We had a nice presentation about soil samples. And each of these normally has a different type of sampling, and each step in this process has its own difficulties. And we also want to have numbers, type, and mass. So that turns out to be quite a mess. We systematically analyze it using the EUQ project, European Quality Control Harmonization, assume reproducible monitoring and assessment of plastic pollution. This is then we had a look into all the full process, starting from survey design, sample collection, sample preparation, analytical detection, and plastic quantification to the end to data reporting. And we also practically applied this in the so-called FACS project, where I will have not the time to present much on. And what we found, we have similar results as in the presentation before. There are many different methods used for sample extraction. Sometimes it's only a digestion process. Sometimes it's linked, for example, for soils with several methods, for example, density separation and digestion, but also pure oxidative treatment. And it's also then the different types of how a sediment is taken. Interestingly, it's quite similar if you go from soils to sediments, but can be different if you go, and also from beaches. If you, for example, have water samples, which is what we mainly do in addition to sediments, it's totally different because we have different type of how we take a sample, but still the chemistry behind after we have the sample in the lab is more or less the same. And with this, I will present a little bit of our lessons learned and what we do in our labs for water and soil and sediment samples, a sample extraction, but also what issues we found, for example, for spectroscopy. So when we have density separation, it was already introduced in the first and second presentation. We aim to float the sample on the surface, so it can, for example, already done with seawater, but also with the different salt solutions. And at the end of the day, the main driving factor is the density and the density of the polymers, how much we can extract. As we've seen already, there are also other methods available. And when we started, we were aiming for large samples. So we used this microplastics sediment separator commercially available. We need 37 liters of a saturated salt solution. We started using zinc chloride and aimed to at least have 1 kilogram of sediments. That worked quite well, but then we had the issue, we have only 20 grams of sediment to analyze. It doesn't work in the MPSS. So we had a joint publication with Thomas Mani and the University of Basel with Patricia Bucaton, how we can simplify this process. So we changed to Erlenmeyer flasks. Much easier to have, every laboratory has them, and we could simply put the sediment inside, sonicate it a little bit, then steer it for 1 hour and let it settle, and then add more of the solution and collect all our particles as an overflow onto these onto a normal glass dish, and then filter it on a stainless steel filter and use it for data analysis. So it saved us quite a time and also a lot of hypersaline solution. At the time, we've got the issue that zinc chloride is not optimal. It has an environmental hazard, and we switched to sodium bromide, which is considered less harmful depending on which security data sheet you look. And but it's worked out quite well. It has a better viscosity, so it's easier to filter. And we also changed a little bit the bottles. So we have now straight net bottles, so-called less nitration bottles, which are even more effective than the Erlenmeyer flask for overflow, and we can simply reuse them several times and can run this process up to 6 times in a row. But also the results we find have a higher number of smaller sized microplastics. So if we compare the same samples of the same area, taken the same with the same sampling crews, we found that we have higher numbers in microplastics, but also higher polymer diversity. So using this smaller sized sampling devices was extremely efficient. It also allowed us to create the layers of the different cores which were taken. So it was extremely useful. And for example, we teach now this method within the GREENLand project because it's easy to transfer to other laboratories due to the easy available devices. When we analyze the sample, we aim to go for also Fourier transform infrared spectroscopy. You hear it already in the first presentation. We use the samples concentrated on a filter. Here you see an example of a sediment sample of our early works, where we had always the issue to have this coffee ring effect, which we nowadays avoid by a special filtration setup, which I can provide you the details on upon request. And we can use it in different modes. What's a good thing about this, that we already heard it, is especially useful to identify the different identities of a spectra. So I will skip this slide. And what we do here is we work mainly in transmission, having this sample in the middle of our sample beam, and then everything moves to a detector. In this case, it's a focal plane array detector, meaning I get a chemical image, then looks exemplarized here like this, and in each dot we have a spectra, which we then analyze. We spent quite a lot of time in the beginning to manually click at highlighted areas in these fields, then checking this spectrum manually, but we said early that this is too slow, and in 2018 published our so-called automated analysis, which is currently still the basis of our analysis we're using, while we also still look for more improved methods. And we use here a correlation with the original spectrum using vector normalization. And the second step is then to match the second time with using the first derivatives and vector normalization. And only if both yield the same polymer type identified, we count it as identified. Otherwise, it is not discarded because it could be something different. Then we have also the ability to transform everything into images and, for example, transfer it to simple for data analysis, meaning we have a direct overview about our databases and the spectrum we have it assigned to, which is extremely useful, especially for hyperspectral data sets. And if you're more interested on simple, it's available with the databases free of charge. Just go to our homepage and have a look. So this more or less already simplifies the process. Oops, there's something gone wrong here. And we use the system, then use it into put it into simple, and then do image analysis using Python and simple ITK. So this was a process we used in the past years. And then we could transfer it already to different IR systems. So using all available instruments on the market, we had access to. At the moment, they're even more available, but they are a little bit more difficult to transfer the data. We're currently working on that. And you see here it worked quite well. We found microplastics in every sample and could also identify it quite well. So we're not limited to a manufacturer. And for example, if you have another system, example the one from Shimatsu, just contact us. We try to figure out a solution here as well, and how to implement your data into our software. If we were using this software, we were really surprised that it's really identified all particle in every sample, but also with a really high success rate. So we only had low error values, but still we ended up around 5% misidentified, but this is the limit we have set for accuracy of our automated data analysis. What lessons learned with this system? So we had a comparative study or a year-long assessment of wastewaters from 2 different wastewater treatment plants. And at some point, for one of the treatment plants, we were running into an issue. We had this type of filters. So you see here, this types of sheets, barely visible, but also when we had identified them, they're partly identified as acrylates, pure varnishes. So different types of materials used for example, plastic windows, but also for sealings and coatings. And we were a little bit surprised that it were so many. So by quality control, we checked the spectra. Looked to us, not surprisingly, unexpected for this polymer type. And then we checked it with the database, was all fine. Still, we figured that there's maybe a leaf-like structure on this sample. And but we didn't find any typical peaks of biopolymer, like natural polyamides or polysaccharides. So it was not fitting any expectation of a biopolymer. One of the things we thought about is polyacrylamides are heavily used in wastewater treatment plants as water-soluble polymer to focus the precipitation of all the solid materials. We thought about that could be a source, but also we checked what type of plant residues could resist our degradation process. So we checked again, checked literature, and then we found that plant cuticles can yield as a spectrum quite close to polyesters, polyurethanes, acrylates, and so on. And then we did our digestion process on it as well and figured out that we had just used the perfect isolation process of plant cuticles. So we added it to our database as well as we added polyacrylamides. We're still working on how to remove them best, as we didn't have any sample now with the same issues. And what was the impact? So it was rather large. You now see with the same data analysis, all these fine films are now definitely identified as plant cuticle. Still, we found varnishes as well and other polymers, but you see it had a high impact on our numbers. So, sample with the highest concentration of microplastics that still had the highest concentration of microplastics, but it was significantly reduced by almost half or even stronger. But each other of the samples was affected as well. But still, we found most of the polymers. We also found, but in similar numbers, but also, for example, for this acrylates cluster in much lower numbers. So Second thing we just published a few months ago was the issue of we wanted to investigate krill samples from Antarctica and wanted to have as less digestion steps as possible because we're aiming to analyze the stomachs. So they were dissected from the samples and then put into KOH and directly put into an analytic filter after we neutralize the solution. So you see here, it was a rather simple setup, and then we ended up with 5 to 90 microplastics per individual. And this is rather high, it was completely unexpected. But only as I had a look into the filters, you see here barely visible the stomach residues, but sometimes we had this kind of film formation, which was rather obvious, where we could say, okay, this was a pooled samples up to 10 of the stomachs, so that was not analyzable at all, but even if we were at low numbers. And then we checked all of our chemical digestants, and some showed these kind of mega particles, which really hinted to have that we have a film-like structure. We investigated this one and figured out that these two types of films are linked to different types of stearates. So we had the fatty acids still in our sample, and they still could form a thin film on our particles, hampering or overlaying the analysis. So we had a high number of false positive results, and then we figured out what we can do. So we did another chemical treatment, but also used the different different digestion process. We added hydrogen peroxide afterwards and used the cuticle database, and then we were able to successfully analyze the samples, but the numbers reduced from 5 to 90 microplastic particles for an individual sample to 4 microplastics in total in all of the investigated species. And this has a rather high impact. And what the main lesson learned here was always add an extra filtration step after you digested your sample, just to remove any residues of your sample, of your digestion protocol. When we now go for the available, we directly using simple business process as we introduced our pipeline now into simple available. But this is available upon request, so drop me an email if you're interested in software. We would have figured out, I think, most of the issues a little bit faster if we had it directly in simple, but as we now avoid this image analysis step and have a direct link between all the data. So we had also heard today about nanoplastics. We also work a little bit on nanoplastics, or we have a dedicated instrument for that. It's the nano FTR. You see here, it's a lot of protection against particles in the air. We have a HEPA filter, a climate system, and another laminar flow cabinet on top of the instrument. So this is how the instrument looks like. And it can use 2 different modes. So we can use, we have a laser giving our signal to the sample, which has a link to an AFM tip. And then yield or spectrum, which we then can transform feature. Better have a broad laser, then tune differences. And with this, we're really able to, for example, distinguish here between LDPE and Riverine, also in polystyrene. As you see here, we have made a cross-section analysis. These 2 signals of polystyrene and LDPE, where we will distinguish along this transect. And also, we can then check, for example, how is the resin stick directly used? Found this flask on the beach of Helgoland, and luckily I just recognized that I had the same currently in the office, that we had one of this flask. The cap on it, both of this flask, so we to identify. We then moved with our system on it. And you see here the country level, and then we try to measure the surface area. So you see here the unweathered material and the weathered material, and as we heard already today, the surface properties are extremely important. You see it's crackle, and I think we lost already a lot of small particles. But if we want to the spectra, more like the same, even on this small nanometer scale between weathered in orange and the new material in black. You see more or less every signal is present just here. Could be one turning up, but as the lasers and limited, we could not measure further down. Still, it shows that it's quite important. But as you see here, for example, against the reference PT, we have this some signal left here, so it can be either from the measurement, but also maybe a hint for other additives. What the most problem is how to correlate and find your samples back on a filter if you use one or more instrument. And here we had the this important project with the Fraunhofer ISA in Itzehoe, where we developed filters and now have a follow-up project to commercialize these ones with a dedicated coordinate system on it. So each of this hexagon is an active filter area, and then it has a number. For example, this one is 119, and then it's here would be 2, 18, 220, and so on. So you always can find by counting your hexagons where you're exactly on the surface, without having the use of any tags or anything else. But also there are dedicated features here on the sides to really put it, you see it here, always in the same position on a membrane, on a holder. And we also have a specialized holder which we can use between all of our systems for analysis. So at the end of the day, we can measure always the same particles and find these back, for example, with Raman microscopy, and then afterwards doing an AFM analysis with a particle size, but also material type, which was in both cases here polyethylene. And with this, I come to the end of my presentation. Is it now a big issue? Yes, we have still many challenges, but on the other hand, we can now see with harmonized analysis the impacts of sampling and sample extraction features, but also the impact of natural materials which we didn't expect to be there. For example, like this cuticle from plant membranes, but also fatty acids from digestion protocols of highly protein and fatty material-rich samples. For also nanoplastics analysis is still in development, especially from the sample size and for particle-based analysis. And with this, I think all my co-workers at the Institute, but also as we have so many collaborators and co-authors of different publications, I want to thank them all. Also the project partners, also many different projects we had or ongoing, but also currently the funding agencies for GREENLand, the European Union, but also for the European Charm project and for the Plastic Interact project, which will have a closer look onto the nanoplastics. And you for your attention and other related questions, just drop me at the end of the webinar a note or speak up. And thank you for your attention.
Dear Sebastian, thank you very much for your great presentation and for sharing your results with us. So we can go on with our next presenter. Our next presenter is Dr. Anja Bubik. Dr. Anja Bubik has a PhD in biochemistry and molecular biology. During her PhD study in biomedicine, she investigated the biological, biochemical, and ecological effects of cyanobacterial toxins at the National Institute of Biology, focusing on their effects on normal and tumor human astrocytes in vitro. After completing her PhD, she joined at the Faculty of Environmental Protection, where she works as a senior lecturer and researcher in the field of health and environment. Her research interests are focused on the study of potential hazardous chemicals and their impact on various environments. She is involved in the implementation of several professional courses, and as a project leader, she is mainly involved in projects addressing the environmental issue of microplastics and plastics. She is also the head of the faculty laboratory and is responsible for the integration of new methodologies and for the development of the students' practical competencies. Professor Bubik will delve into tracking microplastics in small river environments, providing insights into the specific dynamics and challenges of monitoring microplastics in smaller aquatic systems. So, dear Professor Bubik, the floor is yours. Thank you.
Okay, thank you for the nice introduction. Now I will share my screen. But I think Mr. Liam is sharing the screen right now, so I'm not able to share it.
Okay, just a second. Liam, please. Okay, you can now share.
Okay. Okay, is it working?
Yes, it's working.
Okay, thank you. So hello again to everyone. First, I would like to, of course, thank the organizers for the invitation and opportunity to present our work on microplastics. But first of all, I have to say that we are some kind of rookies on that field since we started the deep dive research into microplastics approximately 3 years ago. As they say, my name is Anja Bubik, and I'm coming from the Faculty of Environmental Protection from Slovenia. Since I believe most of you are not very well familiar with our institution, I would just like to make a short introduction of our faculty and give you a short overview of our project related to plastic and microplastic challenges. Faculty of Environmental Protection is quite small, young, and independent, high educational and research institution operating in a quite small town, Velenje, which, however, is the 6th largest in Slovenia. But this makes us no less aware of the challenges that await us as a modern society in the field of plastics management. We were established in 2006 as Environmental Protection College and became faculty 2 years ago. So in 2022, we are offering first and second level Bologna studies entitled Environmental Protection and Eco-Technologies. And both studies are very interdisciplinary oriented and combine different scientific areas. But in all the years of our existence, we are also carefully and consciously developing our project activities, which today are actually one of our strongest assets. Our research group is called Institute for Ecotechnology and Sustainable Development. And as I said at the beginning, for a few years now, part of our faculty faculty's research group has been working on microplastics, which is, as we all agree, one of the hottest topics right now in environmental science. So we decided to address this topic from different perspectives, and therefore we applied for various projects. And I have to say that we were quite successful. So the majority of our projects are and were implemented within the Erasmus Plus program, which aims to raise awareness and improve the knowledge among different target groups. And among these projects, two of them, Microplastics Tomorrow Macro Problem and the GreenLand project towards responsible use and healthy choice of cosmetics, were officially ended last year, so in 2023. But I'm very happy to announce that GreenLand 2, so the continuation of the first project, will start in the upcoming weeks. And there are other two projects which started in 2023. So we are working hardly right now on both of these projects. And today I will focus on research already done and on the research that is planned within the plastics project. So plastics project, the whole name is Plastics Revolution for European Regions. Helps European regions in transition to a circular economy, focusing on reducing plastic waste, improving recyclability, and finding some bio-based alternatives. And the project also addresses challenges like high plastic consumption and microplastics pollution, which also impact climate change. So by sharing best practices and new innovative solutions, plastics project supports also regional policymakers in creative, even more effective policies for sustainable plastics economy. And the goal of this project, which was launched within the Interreg Europe program, is also to place all these ideas, all this research and solutions into the region, into your region. And that's why our faculty committed to contribute to strategic objective for low carbon, green and connected region 2030, with a special focus on water environments. So we decided to conduct the pioneer microplastics and macroplastics research in surface water bodies in our region, with special focus on two main regional rivers, Paka and Savinja, which still, as the whole Slovenia and our region are very small one. So why we decided to address the microplastics in our rivers? Well, microplastics, being tiny plastic particles, can pose a significant environmental and human risk. And they are not environmentally important just to their size and frequency, but the microplastics is important also due to their pervasive persistence in different kind of environments, oceans, rivers, and so on. And those particles or fibers can be ingested by marine organisms and potentially leading to bioaccumulation and biomagnification within the food chain. And additionally, what I really think is important that microplastics can act as a vector of harmful chemicals. So they can absorb and transport harmful substances, chemicals, bacteria, or they can also transport some diseases. And last but not least, due to their small size and widespread distribution, removing microplastics from the environment is still quite challenging and also often impractical. So we believe that monitoring microplastics in rivers is crucial for all risk associated with plastic pollution as a whole, since most plastics found in the marine environment is originated from land-based activities. And here, or whereby rivers act as a major transporting pathways. And we also know that while large rivers may have a higher overall contribution to microplastics pollution, smaller river streams and water bodies play a vital role in understanding localized pollution and in identifying pollution sources. And in addition, some studies also suggest that predictions of plastic emissions from smaller rivers may even be underestimated. And as we all know, there is also a lack of unique methodology for monitoring, sampling, analysis of microplastics, and a lack of standards. So monitoring, or we can conclude that monitoring microplastics in water still presents a range of concerns and open questions that researchers are actively trying to address, right? So sampling and analysis methods, microplastics quantification, characterizations are among the main issues. So within the plastics project, we started to work towards the development of a sampling method that could be a potential alternative to the currently used methods, or can just be the best solution for small rivers. So at the beginning, we performed a detailed article research and an assessment of sampling methods and sample preparation procedures used in studies regarding riverine microplastics to get just a quick grasp of the most commonly used ones. And based on all collected data, we decided to design our own prototype for microplastic sampling based on a filtration system with a portable water pump and with some small upgrades just to allow accurate monitoring of physical and chemical sampling conditions, like, for example, water flow. And we believe that the upside of such a system or such a prototype, which you can see also here on the right side of the presentation, is independence of measurement on water flow and sampling depth, while also having some kind of control on how much water we filter, making measurements more accurate, more representative, and more accurate. And of course, this prototype is very useful because it's portable, it's very fast. It enables us to concentrate larger volumes of waters. And we already performed the first sampling, like say preliminary sampling, and the system really meets our requirements. We were able to filtrate and collect the sample from both rivers, and we found some particles and fibers which were then confirmed using FTIR's spectrometry. And now, what are our further steps? We will now monitor and sample microplastic over a period of 2 years in both of our regional rivers at different predefined locations. And we are willing to determine or identify the impact of specific industrial activities and urban environments on microplastics presence and dynamics in our small rivers. But there is still a lot of work to be done. So I hope in a year or two, we can bring you even more results on and experience on our prototype. So where to from here on in general? Well, with our study, we also try to contribute something positively to the developing of unique methodologies for microplastic sampling in water environments or in small river ecosystems. And of course, we or I believe that all good and reliable studies will lead to stricter policies for pollutants in the future. And of course, besides the research, it is very important also to improve the knowledge and to increase awareness as a social goal. And this is what we are really aware as a faculty. And this is also something we are addressing within both projects. So research part within the plastics project and EDO for Plastic Circular, which is focused mostly on education and raising awareness. So at that point, I would like to end my presentation. It was a really brief one, and I would like to thank you for the attention. And at the same time, I would like to apologize because in a few minutes I will have to leave the webinar because I have another webinar in 10 minutes. So here is my email. If you have any additional questions, I really make really good notes, and I'm really happy to be part of this webinar. So thank you again.
Thank you very much, Professor Bubik, for your great presentation and for being with us today. So if someone has some question, please, you can use notes here, or you can email Professor Bubik. So we are going on with our next presenter. As I said, it's a great pleasure because we have here our project partner, Professor Liam Morrison. So I will ask him, because he's right now here with me, to introduce himself and to share his presentation. So, Professor Liam, the floor is yours. Okay, we will wait for a minute to share his presentation. Okay, we can make a short break for maybe 5 minutes, and we can go on with Professor Liam Morrison for 5 minutes. See you in 5 minutes. Thank you.
Okay, bye.
See you. Bye.
Aha.
Šta se dešava?
Essence. Što je lepa boja? Ovo slikam. Što živi. Profesorka, pravimo pauzu 5 minuta pa ćemo se uključiti za Liamovu prezentaciju. Imali su neki tehnički problema da okače. Ali ne čujem vas, ja morate uključiti mikrofon.
Dobro, za 5 minuta čujem.
Da, samo sam isključila kameru jer su svi sad na ofu. Ali nemojte se izlogovati.
Pa nije, ja sam se izlogovala pa vratila, da.
Dobro, vidimo se.
Tu sam, ćao.
Sure. That's true. Good question. One second.
Are you seeing this? Yes. Perfect.
Yes.
Awesome. I'm trying.
Okay, we're going to go around.
Yeah, okay.
We're going like that again. I think you're there.
I don't know what I'm doing. Stop sharing.
Okay, let's see. And then to move from screen to screen. Perfect.
Give me something. Okay. So,
Okay, I think.
okay, so you need to just, your finger just go up and down, okay?
Dear Professor Morrison is now ready to share his presentation and first introduce shortly himself. And after that, we will hear some US results from their research from University of Galway. Please, Professor Liam, the floor is yours.
Favalavam, is that correct, Natasha? Favalavam? Oh, okay.
Like a close, yes.
Have I two microphones? Okay.
This microphone is on.
Okay. And Dober Dan, everyone. And thank you to everybody at Educons for hosting us today. I'm delighted to be here with my colleague, Professor Mark Healy and Dr. Anna Mendes as part of the GREENLand project, and to talk to you today a little bit about the research that we're doing on microplastics at the University of Galway. And I know some people from Educons have visited us in Galway, and that's been great. But for those of you that are with us today, and I see there's over 30 of us, I'll just tell you a little bit very quickly about the University of Galway. So we're based along the west coast of Ireland. I think it took us maybe about 12 hours to get here yesterday via London. Galway is often described as the cultural capital of Ireland because it's a very nice small city, about 70, 80,000 people. A lot of festivals in the summer, actually Novi Sad, and I'm only here about 24 hours, but Novi Sad reminds me a lot of Galway, and it seems to have that vibe and buzz that these smaller second cities in countries have as well. And also we're very close proximity to the countryside. This is an aerial shot of the university here, and the university forms a major part of our city because it makes up for about 20% or 25% of the population of our city. And there's also the Atlantic Technological University on the other side of the city. So our university was established back in colonial times when we were under British rule as Queen's College Galway, as we then would have Queen's and still have Queen's College Belfast and Queen's College Cork. And we opened in about 1849 with something like 68 students. Today, and this is our particular institute here that we work in, the Ryan Institute at the University of Galway. Today we have probably close to 20,000 undergraduate students and about 3,000 staff and maybe 2,500 to 3,000 postgraduate students. So we're a very large university. In my opinion, unfortunately, we're too big. I would much prefer if we had much smaller numbers of students. So moving on now to talk a little bit about the research that we conduct in Galway. So we look at a range of environmental matrices. I probably should have introduced myself better and say that my own background is in marine science, in both marine biology and in chemical oceanography. And my two colleagues that are with me today, Anna, her background is also in marine biology. Anna is from Portugal and worked both in Portugal and in the Azores, which is also part of Portugal. And Professor Mark Healy, that is with me, is a civil engineer who has worked extensively in water and wastewater and soils and almost every component of the environment out there for a whole range of organic and inorganic contaminants. Just to say, just to show this slide really as part of the triple planetary crisis. So the United Nations and its environmental program recognize that we are facing this triple planetary crisis. And this triple planetary crisis is driven by climate change, loss of biodiversity, and also enhanced and increasing contamination and pollution of our environment. And it is really based on, if you like, the unsustainable development and production of things like energy, chemicals, materials, and technologies. And actually, the Science Coalition now will look at this and say to you, plastics are very much at the center of this because plastics contribute to climate change. If we look at greenhouse gas emissions, I think in about 2015, about 4 to 5% of greenhouse gas emissions were driven by plastics. And the majority of that comes from the production of plastics. And it goes through every stage of the life cycle of the plastics as well. So from the sourcing of the raw materials to the wastewater management. We're also seeing scientific evidence now to suggest that microplastics and plastics are impacting on carbon storage in soils and also in marine ecosystems. And also the albedo effect in places like the Arctic, where particularly things like tire wear particles, which are also plastics, are decreasing the cryosphere light absorbing properties. And we also know a lot about their impact on keystone species. And that's not just on vertebrates and invertebrates, but also on our very own species, humans. We're now beginning to see much more and more studies that are showing us the impacts of these, whether they're at the endocrine level, the cellular level, the reproductive level, the physiological level, whatever level they're at, they're getting into our systems. Also, and I know we're going to talk more about this, also in terms of our landfills and our dump sites, they're increasing, and they're increasingly covering larger areas of land. And we have a resulting impact on species and species composition. And I don't need to tell any of you about the role that plastics are playing in terms of leakage of organic and inorganic contaminants, and also in terms of being vectors of contaminants. And I suppose my presentation today is kind of it's a general presentation, while it's also covering the research we do at the University of Galway. But you know, I'm almost a half century old, or you know, a few years short of it. But I think it's fair for me to say that we actually live in extraordinary times, absolutely extraordinary times, between global pandemics and wars and everything that's going on in our own countries. And I suppose you only have to look around us here today. Practically everything around us is made of plastic or metal. And if we lived 100 years ago, everything around us would be from natural components, whether it would be wood, wool, rubber, etc. But even our clothing today is made of plastic. And I suppose the COVID-19 pandemic also brought it home to us, the importance of plastics and the societal benefits of plastics and how important they are, because, you know, they were able to provide us with that protection that was necessary for people. But I think what we will go on to see in the coming years, and these scenes are very common now, this is just from some beaches in Ireland, where you see lots of plastic material washed up on the shores. And this is now a global challenging issue on a kind of a transboundary scale. And a lot of the initial research focused on the oceans, and a lot of the majority of the publications that came out about microplastics were about the oceans. But most of all of the plastics, like mold contaminants, originated on land as a result of human activity. And I suppose these were all familiar scenes to us during the pandemic, where we saw that all of this PPE was plastic. Most of it was single-use plastic, which is one of our biggest problems. And if we also look from Eurostat and look at the projections, we can see that more than half of all the plastics that were ever produced on the planet were produced since the year 2000. And the projection for those production is that increasing trend that we will see as we have a global population increase as well. And I think one of the most frightening statistics for me is that plastics is about 100, 120 years old. Huge volumes of it have been produced, but about less than 25% of it that is produced today is recycled. And only 9% of all the plastic that has ever been produced has been recycled, about 12% has been burnt, and the remainder, almost 80%, has ended up in our environment and in our cells. And for me, that's, you know, unpleasant. And also, I'm not embarrassed to say, but I'm ashamed to say that Ireland are one of the highest producers of plastic waste in the EU. And to actually make that worse, we are probably the fourth worst in terms of recycling rate. And that's just from the statistics that Eurostat have provided us with. Now, to talk a little bit about the work that we have done in Galway, well, I think understanding sources is a key factor that's very important when you consider microplastics. Because if you want to actually look at mitigation strategies or environmental protection strategies, again, reduction in sources is very important. So understanding sources is key. And in Galway, we have a range of facilities that are suitable for the analysis and determination of microsamples or microplastics in samples. We started out as trace metal chemists, so we were pretty pedantic about cleanliness and contamination, and we were also marine trace metal chemists, so a lot of the work we were doing was working at very low levels in seawater. So we have an ISO 7 and an ISO 6 clean room with extraction facilities there. We have a range of cabinets. We're continuously developing and altering and changing our operational procedures in terms of our gowning and looking at our controls. In terms of instrumentation, I have to put my hands up and say I can't compete with my colleague here from Germany on that. We have a confocal Raman system with a 532 laser and a 785 laser. And we also have a new Shimatsu FTIR system, a micro FTIR system. Within the university itself, we also have scanning electron microscopy and transmission electron microscopy. But when it comes to the nanoplastics and the microplastics, I'm afraid I have to defer to my colleague here on that. So looking at PPE as a source of microplastics, and this is just during the pandemic, something we Anna did, in fact, was looking at layers of masks. And I mean, other people have published this. I think there was a rush to publish this sort of stuff when it came out. But again, just to show, the sources and my images, because I'm on a different screen here, my images behind me are just microscopy images. But these layers of these masks are basically made of polypropylene. And some of the statistics that were very interesting for me in terms of the pandemic and microplastics was that in England alone, about 2.3 billion tons of single-use PPE was distributed to the social care services between February and July 2020 at the start of the pandemic. And that was equivalent to the same amount that was actually distributed in the entire previous year. And I think if you look at face masks, about 129 billion face masks and 65 billion gloves were used every month during the pandemic. And what's even more frightening, which will give you the extent of the production of this plastic PPE, is that the market was worth about 800 million in 2019, just before the pandemic. But in 2020, that market was worth 166 billion, opposed to 800 million. And I suppose if the patterns continue and the disposal of that, we're going to see a clear record of that in our environment moving forward. So I want to talk to you a little bit now about a particular research study that we conducted at the University of Galway, where we looked at wet wipes and disposable wipes as a source of microplastics in the ocean. And again, these are non-woven textiles that are used for health and hygiene and sanitary reasons. And about 1 million tons of these are produced every year across the European Union. In most cities in the world, they are associated with the blockage of sewers, because when they get into sewer systems, they form ropes. They usually combine with oil waste and vegetable oil waste from restaurants, etc., that's in the sewers, and they cause major blockages. They're a huge problem in places like London, and they caused 75% sewer blockage in our own city in Galway a few summers ago. And they're also a consistent feature of surveys, monitoring surveys that are carried out internationally by organizations like Coastwatch, particularly in the Thames estuary, places like this. They're the most common litter or debris that are actually found in these surveys on our beaches globally. So here in Galway City, this is a picture of me holding up a mass of these wipes. So what happens in Galway is, and this is Anna and another student, and all along the beach here, you can see where these have been deposited. And what happens is these large deposits wash up and they're intertangled with seaweeds. And these are not just wet wipes, they're all types of sanitary products, everything from sanitary pads to suppositories to tampons to condoms to, I mean, I'm amazed at what people actually flush down toilets and what actually source systems cope with as a result of that. But with heavy rainfall, we have a number of combined sewer overflows in the city, and these are common to all cities. So during periods of very heavy rainfall where the local wastewater treatment plant would be at capacity, these sewer systems would be opened and they would release the untreated waste into the sea. And the wipes in the ocean would then combine with seaweeds and wash back up on the shore. And like all the processes of fragmentation and degradation of plastics, these form then microplastics. And this is just to show you an example. So we then went into, and in Serbia now I can probably name them, but when I'm in Ireland, I cannot name the retailers or the high street shops that we went into. But we went into all of the supermarkets in Ireland. We took their brands of flushable and non-flushable wipes and sanitary products. We brought them back to the laboratory and we analysed them. So here you can see on the top left, you can see a commercial wipe. This is a Raman image of it. And this is a commercial wipe extracted or a fibre extracted from a sand sample on a beach near a wastewater treatment plant. And again, you can see down here very similar imagery for wipes. And when we look at these, we find that they are made of plastic. Even the ones that are described as flushable wipes can also contain cellulose and microplastics. In fact, there's no such thing as a flushable wipe. All wipes must be disposed of in landfill waste. And one of the things that we found really, and again, it comes back to human behavior because that's one of the challenges for the plastic pandemic, if you like, is a lack of awareness among people regarding the adequate disposal of wipes. And this may be due to something like improper labeling of products. In fact, when this paper was published, it made the local media, the national media at home, and a number of supermarkets in Ireland released statements, including Aldi, to say that none of their wipes contained microplastics. And it simply wasn't true. But it wasn't for us we couldn't name in this study. Sanitary products are probably very much overlooked and are certainly an unaccounted source of microplastic fibers in the marine environment. Wastewater treatment plants need to look at measures and strategies that will be aimed at mitigating for this to stop these overflows and the discharge of them into our environment. This was just the graphical abstract from the paper we published in Water Research on it, and that's just a copy or a screenshot of the paper. We're currently working on a number of projects which we have linked in with the GREENLand project, and one of those that Mark is involved in, and Anna, and we have a PhD student, is looking at the application of manure in Ireland and the microplastic content of that. Because most, alongside human waste, I think it's about 75 to 80% mark of human waste in Ireland is actually applied to land. So chicken manure, sheep manure, and cattle manure would also be applied to land. It's often referred to as organic manure or organic fertilizer as opposed to your chemical synthetic fertilizers. So we're looking at the microplastic content of that. and doing a number of experiments to see is that safe and is it appropriate to be spreading that on land in terms of its microplastic content. As I said, that covers both cattle and sheep and chickens. It doesn't come without its own challenges because, as you will know, one of the major challenges in the analytical procedure for microplastics is the digestion of organic matter. And boy, is this organic. And it has plenty of organic matter in it as well. Mark, also a previous PhD student of Mark's, had a project ongoing with Anna and Nessa that were looking at microplastics in synthetic fertilizers and comparing this with the microplastic content of organic waste. And we also currently have started a new project with an MSc student where we're looking at microplastics in landfill leachate. And particularly as part of the experimental design, we're looking across a range of different types of landfills. So we have lined landfills, unlined landfills, or mixed. We have legacy landfills and we have operational landfills. So modern and older landfills. And I suppose one also area of research that's close to our hearts, and particularly Anna's, is at looking at microplastics in marine turtles. And I know a lot of research has been conducted in the Mediterranean where they are used as sentinel organisms as regards microplastic contamination in the waters there. But turtles wash up frequently on the west coast of Ireland. So what happens then is they tend to get caught up in the North Atlantic drift. They get washed into our waters. They usually are cold stunned because they're not used to those temperatures, and they may not feed for long periods of time. So Anna and a previous student, Alina, and this is an example here, I think, of a leatherback that has been washed up along the coast. I think we have around 20 of these turtles in cold storage. They're internationally endangered and protected species, so a license is required to work on them. And we have been developing protocols to look at effectively and, properly extracting the microplastics from their digestive and intestinal tracts. So Anna has been making up what we call a mimic chine, something that actually mimics the contents of their stomachs. And this here is a picture of the intestinal tract and some of the work going on in the laboratory. And Anna made some very interesting findings here. So we noticed, in particular, when we moved from one scientist in the clean room, from 2 to 1, that our blanks and our recoveries were much better in things of contamination. We've also worked on sediments in the past, just some publications we've worked on there. We've also worked with a group in Iceland, our group that were working in Iceland, looking at sediments in terms of oceanographic processes and distribution of sediments there. Anna did a very broad survey of microplastics in Ireland from all around the coast as part of a government-funded project that we did as well. We've also previously looked at deep-sea mesopelagic species of fish, which again brings home the story of these microplastics are everywhere, from the mountaintops to the ocean basins to absolutely everywhere. And one of our most successful papers in terms of citations was work that Mark and I did previously with others, looking at microplastics in biosolids or sewage sludge and looking at the effect of different types of treatment on that, whether it was anaerobic digestion, lime stabilization, or thermal desorption, and what impact that had on the particles. And I just want to give a plug in here, particularly given that Aleksandra is with us today, colleague of mine from the COST. I head up a group in the COST, a working group looking at monitoring and sampling of microplastics. And we last year produced a paper on extraction methods and invited a review of those. But from our recent meeting, we are also now looking later this month at producing something similar in terms of a collaborative review on the avoidance of contamination within the research area. And I'm reaching out to all of you here today in this meeting to say you're very welcome to join on this as well. We're working with Javier in the Canary Islands and Thomas Miesel in Austria and some other people as well, and Aleksandra and Zahida. And we're very open to partners on that as well and tying it in with our GREENLand project. Thank you very much.
Dear Professor William, thank you very much for your great presentation and for sharing your results with us. I want to check, is Professor Stefan with us, because he sent his presentation and I can't see him here. Maybe he has some problem with connection. No, he isn't here. So this was our last presentation for today. And now you have 15 minutes, 30 minutes maybe to ask your questions. Our presenters are still here, except Professor Bobik, but if you have some question for her, you can send to us and we will try to get an answer from her. So please, if you have some question, please raise your hand and we can start with questions and suggestions. Okay, Joanna said, thank you for all the talks. Also, we have a comment from her. It is all super interesting. Will it be possible to access the slides later or links to those papers? I suppose Professor Liam is a question for you. Joanna is asking for links for these papers, but we can send your presentation. We can put it on Google Drive, so you will have opportunity to see these presentations. Okay, we have Cleo Stratman.
Hello, can you hear me?
Okay, Cleo.
Thank you so much. Thank you so much for the great presentation.
I can't hear you, sorry.
How's it now? No.
Okay. Can you repeat your question, please?
Can you hear me now?
Yes.
Okay. Sorry for the technical troubles. Thank you so much for the presentations. I couldn't join the whole webinar, but I followed Dr. Liam Morrison's presentation, and I was really interested in whether you have worked more with industry on the issue of wet wipes in the sewer system, and if or whether they are planning to or investing in this problem, maybe talking with politicians or producers of wet wipes and educating consumers not to throw things in the toilets, for example. And I'm sorry, I'm a researcher and environmental consultant.
Thank you, Theo. Yeah.
Liam, we are not hearing you.
Yeah, thank you, Cleo. I was invited actually after the paper was published to give a presentation at a zero pollution conference in London. It was during the pandemic and it was an online event. But there were some people there from the Sydney Water Authority who had done a lot of research on wet wipes, and they weren't looking at them in terms of microplastics. Our study was the first study to do that, but they had been looking at them in terms of the blocking of sewers. And one of the guys there brought up that day, which I didn't actually know, I didn't believe it at first until I Googled it afterwards, was the influence of celebrities on people using wet wipes. Because if you had asked me as somebody who had small kids at the time, I would have thought that the biggest consumer of wet wipes were parents with children, but actually not. The biggest consumer of wet wipes were male 18-year-olds between the ages of 18 and 35, because a well-known famous American rapper and movie star called Will Smith had declared a year previously that you are not adequately hygienic enough unless you were using wet wipes. And I thought, oh no, this cannot be true. But actually I Googled it and there it was all over the media. And I Googled it again before I came here this week in case I was asked this question. And that was one of the strongest So influence was very strong, and the Sydney Water Authority were trying to counteract that. Across Ireland and the UK, we have a campaign called the 3 Ps. So there's only 3 things that go down toilets: pee, poo, and paper, and absolutely nothing else. But from having visited the shore with Anna and having, sampled this waste, the materials that we have found, including things like disposable men's razors. I mean, who flushes those down toilets? But some people do in Galway. And there is a lot of research into trying to develop flushable and more sewer-friendly forms. There are even ones out there called Just Water, and those that are just made of natural materials and contain nothing else but water, but we've actually found different.
There are not lots of plaques made of bamboo, but they have with some kind of polymer also.
Yeah, my colleague Anna is saying that there's lots made of bamboo, but they also have polymers associated with them.
Oh, thank you. 1,000 thanks. That was a really great answer. And maybe I can send you an email if there are more information we could exchange on. I think it's a very important topic. And thank you so much. And super surprising that this is a large consumer group who are mismanaging those wet wipes. Yeah.
Thank you.
Sorry, now I can see that Professor Stefan is here with us. So keep your questions for later, maybe to give him opportunity to present his results. Professor Stefan, do you hear us?
I hear you well, yeah, and sorry, the invitation I got was for GMT +2, which starts now, so.
No, it was 2 hours ago, but everything is okay. Professor Stefan Krause is maybe a short presentation for others. Professor Stefan is a renewed professor of ecohydrology and biogeochemistry in the School of Geography, Earth and Environmental Sciences. He is a part of the Birmingham Plastic Network, an interdisciplinary team of more than 40 academics working together to shape the fate and sustainable future of plastics. The unique team brings together chemists, environmental scientists, philosophers, linguists, economists, and experts in many other fields to holistically address the global plastic problem. Professor Krause will explore the drivers of Riverine microplastic fate and transport. This presentation will provide an in-depth look at how microplastic move together to river systems, shedding light on the factors that influence their distribution and accumulation. So please, Professor Stefan, you can share your presentation, and the floor is yours. Thank you.
Great. So I'm sharing my, apologies for that. This came through on my calendar as basically starting now. Can people see my presentation now?
No, we still cannot see your presentation.
Oh, let me start again. So I'm in the mode of sharing my screen. It is telling me that my screen is shared, so that's not the case?
I can't see it.
And now apparently I can't make it, I can't... I did send you my presentation as well. Do you want to share it otherwise?
Yes, okay, I will.
I received an error message only now that I don't have permission to share my screen, so probably that was an issue. I mean, either you share my slides or if you give me permission to share, I can try it again. Oh, perfect. Thank you. Could we go on presentation mode?
You can hear me. I have a problem with presentation mode on this computer, so we can try on this way if you.
Okay, that's great. Okay, then let's start like that to not lose more time. So yeah, apologies for apparently being late. Then, what I'm trying to talk about in the next 10 minutes is things we start to understand about what drives riverine microplastic fate and transport. Given that a lot of research has been done in the last couple of years of how microplastics are transported from terrestrial surfaces and increasingly also from the subsurface to the ocean. Excuse me, if we could go to the next slide, please. And I think it's fair to say while we have developed as a community over the last couple of years a relatively decent understanding of where mismanaged plastic waste is generated on the continents and where it is accumulated over time, as it's showing on the left-hand side. I think it's also fair to say that under our understanding of how rivers are actually transporting plastics to the ocean is still very limited. And I use the example of a recent study on the right-hand side. Some of the people I know very well and I would call friends, and so I don't want to criticize their work at all. I think that it's showing just how we are still learning as a community, and it's summarizing basically how a couple of years ago there was a wide understanding that it's probably 10 or 20 rivers that are contributing up to 90% of plastic waste ending up in the oceans. Now, a year and a half ago or 2 years ago, a new study arrived, including a same large proportion of the same team of authors, probably rather 1,000, maybe more than 1,000. So, we are jumping orders of magnitudes, and I think that's highlighting that we are still in the process of learning what's actually happening to plastic waste ending up, in particular microplastic, in river catchments. And if you could go to the next slide, please. One approach we are taking when we think of how plastic waste ends up in river networks, so really thinking about the sources of plastic waste and how they get activated, because not all of them are always activated and actually connected to surface water bodies, and then how plastic waste is propagated in often dendritic river networks. We take a catchment approach to that, which is or perspective, which is nothing new really. That's something people have done for other contaminants for a very long time. And if in the next remaining 7-8 minutes I manage to bust free of the plastic myths, as we call them, I think that I would call that a success today. And that's to show that the majority of plastic waste is by no means accumulated in the world oceans. So while there are some sinks, the majority of sinks, including the oceans, are temporary sinks and not permanent sinks. That river catchments are definitely more than just conduits of plastic transport. There's a lot of time, a long residence time in rivers where things are happening to the plastics that are transported in the oceans. And we had a lot of discussions, particularly with oceanographers, that where there's still a widespread assumption that it's weeks, months, maybe very few years that plastics reside in river networks. I'm going to show you in a couple of minutes that it's significantly longer. If we could go to the next slide, please. We do a lot of field work on this, but I want to use a model, and our model is as imperfect, if not more imperfect, than many of the other models, global plastic transport models that are used as well. We use the Hydro Rivers Atlas, which is a really great data source providing physical information like the width, the depth, the slope of every river section worldwide, and calculate based on using similar assumptions as most other global plastic transport models are doing of distribution of mismanaged plastic waste based on country-specific emission data and waste handling data. What we do slightly different is we distribute these amounts of country-specific mismanaged plastic waste based on population density information of that countries, as well as land use information. And we distribute that to stream sections taking distance to each of the stream sections into account as well, and then we route using something that is not new. A lot of the sediment transport information that we use in other sediment transport models to route particles of 0 dimensions. That's very similar to other global transport models, taking into account river management as well. And if I say we, that is done together with Professor Jesus Gomez-Velez, who did that when he still worked at Vanderbilt. He's at Oak Ridge National Lab now. And if we quickly jump to the next slide, please. The insight we get into global plastic waste distribution with that on land, this is not transported plastic yet. This is just the plastic emitted that you see on this slide. There are a couple of really important insights emerging from that. One is that the majority of plastic waste is by no means generated in the first 50 kilometers away from the oceans, which is what a lot of other global studies are focusing on. I think what we are showing, and you see that in the subtiled C, I can't animate the cursor here now, is that the majority of plastic waste is actually generated in the first 1,000 kilometers of rivers before they discharge into the oceans. But if you look on the bottom, that really boring looking gray and black bar charts there, one really important point we want to raise also is that a lot of plastic waste is generated in rivers that are endorheic. That means they never see the sea. And this is based on which rivers naturally would be endorheic, of course, by over-obstructing. The Colorado River is a good example for that, by over-obstructing flow from many of our rivers, many Mediterranean rivers as well. A lot of them don't see the sea anymore, and so we need to start thinking what happens to all that plastic waste, all that particles that end up in there. If you go to the next slide, please. The other, if you focus on exorate basins, the other finding with this very simplistic global model that we made was that actually, if you look in the left part of that slide, you see the amount of plastic waste generated in small, intermediate or large river basins. And what the red and blue parts are showing is which of that river basins are free-flowing and which are heavily managed. Heavily managed meaning they have river reservoirs and dams. And we know that dams are trapping a lot of sediments. I show you just one of the many pieces of evidence, field evidence, in a second. And what's really interesting there is if we look into which of that plastic waste can then actually be transported through rivers. Is it really, does the majority of that sit in large river basins? Yes, large river basins, non-surprisingly, also see the largest accumulation of mismanaged plastic waste, but the largest amounts that are free-flowing. So in rivers that can transport plastic waste, like other sediments, to the oceans, occur in intermediate basins. So if we look into the 20 rivers on the right-hand side that were attributed to be the largest contributors of plastic to the ocean, only 2 of them, the Amazon and the Congo, are not significantly managed in their flow. And I've just been back from last week. I spent a lot of time at the Yangtze, which is indicated as the largest contributor of plastic waste to the ocean in several studies. But it's also, I mean, we have the 3 gorgeous dams. We have lots of dams upstream of that. It's heavy flow modulated. So I would really doubt how much these large rivers are contributing to the oceans. It doesn't mean that plastic waste pollution is not happening there. The evidence for that, if you go to the next slide, we looked into many reservoirs and dams and their impacts on rivers, from large rivers to really smaller ones. This is one closer to home. I work in Lyon as well, and what we have flowing through Lyon is the Rhone, which is one of Europe's largest rivers. It's also one of the most heavily managed rivers. And as you can see in this black triangles, they indicate the location of reservoirs. They are mainly there for flood protection along the Rhone. And at the upper part of the Rhone, between Switzerland and Lyon, you also have what we call the plastic valley. So there's a majority of plastic production in France and even in Europe is happening. A lot of industries around there. And if you look on the right-hand side, that bar charts show you if you go from upstream on the left to downstream on the right, the concentration changes of plastics in the sediment. And indeed, wherever you have reservoirs, they are dropping, unsurprisingly, downstream of the reservoir to virtually 0, and then they start to increase again. So the transport really overrules the spatial patterns of sources here. There's another process, if you go on to the next slide, please, that we often keep to ignore, and that is that we don't only have transport based on the physical properties of plastics that define what is suspending in terms of sediment and what is settling by gravity. When we did large field studies, global studies as well, we find huge amounts of low density plastic in streambed sediments. They should be floating or being in suspension. They should, if you only think of gravity settling, they should not be at great depths actually in sediments where not just us, where the whole community finds them a lot. And we did a couple of studies over the last years, including modeling studies as shown here, but also flume studies, where we have been highlighting that in particular for the smallest of the microplastics, and when we go into nanoplastics, accumulation through another process, hyporeic exchange, where we see advective forcing of particles into the porous matrix of a stream bed, can be really dominant, can dominate actually over gravity settling, and can trap particles for much longer in sediments than if they would be just falling out by gravity and sitting on the top of sediment. And Jen Drummond published a couple of papers with a former postdoc in our group on that in the last years. And while she found there was a wide range of travel time of particles, the average of that would be 7 years per kilometer through a river network. And if you go on the next slide, that basically means if we run this for large river catchments like shown here on the right for the Ganga basin or for the Mekong on the left, that residence times are really long. If we look into mismanaged plastic waste emitted into that basins for 70 years since the 1950s, we quantify that less than 3% have actually exited out into the ocean. The simulations that we have there, the emission rates are pretty similar to what others have found in their global models, only we show more than 97% in both cases are still sitting in that river basin. So we really need to think about this legacy that we are creating there. If you finally go to the next few slides, please. We use observational data, like this is observational data all along the Ganga, to actually highlight how important, highlight how still uncertain a lot of our models are, in particular the large-scale models, but also how important hotspots of plastic emissions are. But in contrast to many other contaminants where we see emission hotspots here having, like you can see in the mid-sections here, for instance, of the Ganga, having a really long downstream footprint. If you look here in this red spots in the middle, just a little bit further to the east, so that is downstream in that case, you see concentrations being pretty low again, so that the footprint is really small. And if you go on the next slide, one of the reasons that we find for it is not only that you have reservoirs, and I come to the last process I want to highlight here, that are causing this really tipping points in concentration changes that we are finding, but we have another process that we often keep to ignore. We ignore that in our model as well, and that is that a huge amount of water is abstracted from rivers, either for supplying water for communal water use, or using it for irrigation and agriculture. And that's something that we see in the patterns at large rivers, but that we could only quantify so far at a much smaller scale. And I come to my last example here on the next slide, please, where we worked with colleagues from the USGS in Denver and Boulder, Colorado, on the Boulder Creek and South Boulder Creek, which come from, so it's much less polluted than the Ganga, where the slide we saw before. Two streams that come out of the foothills of the Rockies. There's not much and not many people living upstream of Boulder in that catchment. And we quantified concentrations in river sediments and in the river itself in both streams, and compared that to population density. But also, if you go on the next slide, we looked into the impacts in particular of obstructions that are happening there for agriculture. And if you go on to my final results slide here, what we could show is that these obstructions, when we calculate, not only when we don't focus only on the concentrations, which are really important for exposures, but when we want to quantify downstream exports, it's the loads, the particle loads that we are interested in. And then these obstructions are actually leading to significant transfer of particle loads out of the catchment area, even into different catchments, as you see that for South Boulder Creek, right in the upstream part, as well as in the downstream parts, that slightly shaded areas are indicating the volume of particle loads that are actually moved out of the catchment even. For Boulder Creek in the downstream section, half of it is moved out into a different catchment where it's used for agriculture. So the assumptions that all of our global models are doing, but even river-based models that are just based on a single catchment, that we have a dendritic flow, a convergence of flows of not just water, but also the particles transported with it, they are often not true, in particular where we're messing around with a water resource management. That is true for many of the largest rivers worldwide, but also some of the smaller ones. And it's something that I think if we really want to predict accumulation and transport and the fate of particles in rivers accurately, we really have to make that move to include these processes. So yeah, with that, thank you very much. If you just go to my final slide, thanks for your attention. Apologies for being late. Yeah, hoping we have some time for questions.
Thank you very much for your great presentation, and sorry for misunderstanding about time, but we will send you a recorded meeting version to all of you. So please just write your email addresses for all of you that you wanted to receive our presentations and with a recorded meeting. So now we have some time for questions. So Professor Pucalewicz wanted to ask or to add some comment on this webinar, so please.
Yes, thank you, Natasha. I have some comments. And thank you to Stefan for nice presentation of microplastic in rivers. I should just to mention that we in our river for Morava and Tara, we have not microplastic, but not microplastic, but microplastic. We have the bottles, so we have big issue with this river flooding with the plastic debris. So my question is for Mr. Primpke, because Mr. Sebastian Primpke, because we all scientists here spoke about microplastic here and there, but what happens with remediation techniques? My question is because I visited Helgoland last year, and I know that they have a long time experiment on degradation of different polymers in seawater. So I wish to know, do you there have some results about consortium of microorganisms which is developed on different polymers in seawater? For Sebastian. Can he?
Sorry. Thank you for the question. And yeah, we did some years ago. I can also later send the for the webinar, send the application did an analysis not only on what microbes are forming there, but also full biofilm for this experiment. Just to understand for everyone, this experiment runs now for 10 years, and it simulates plastics on the bottom of sea surface, meaning there's an exclusion of light. To also have this conditions not only on the surface, but what happens when it sinks down. And we tried now several times to find first impacts of degradation, but for most of the polymers, there's not much happening if you exclude light. But you have strong biofilm formation, and this biofilm was then analyzed also for microbes growing there as well, and also fungi. But you would now need to check what was published by our colleague Ingrid Kirstein. She was doing mainly the work on the biofilms. I can send it to you later. Mm-hmm. But what is the main thing is there is, for most polymers, not much happening Especially if you also look, for example, with techniques like so remove the biofilm and then have a look, for example, with techniques like SEM or AFM. And but some polymers like PLA, which is considered biodegradable, is still existing in more or less intact after 10 years if there's no light and it's not composted at all.
That's bad. Too bad. Thank you.
Okay, thank you, Professor Pucalevich. Thank you, Sebastian. Do we have more questions for our presenters, for Professor Aleksandra Tubić, Professor Liam Mollison, and for Agnieszka Dąbrowska? Unfortunately, and for Professor Stefan Krause, because only one of our presenters is not here, but as I said, you can ask Professor Anja Bubik by message. Okay, if we don't have any questions, I would like to extend my gratitude to all our presenters, our great researchers, great scientists, for sharing their presentation, their results with us. And I wanted to announce a conference which will be held next year here at University of Educons within our GREENLand project, Microplastic-free Environment. It will be in live here in Serbia, in Novi Sad, so all of you will send your invitation for this conference, and we will be honored to have you here with us and to meet you in live. So thank you very much again, and see you soon, I hope.
Thank you. Bye.
Thank you. Have a good day. See you.
Yeah, bye.
Thank you.
Anna wants to say something.
Just bye.
Okay.
Thank you.
Bye.
Bye-bye.
Bye-bye.
Goodbye.
Bye.
Bye. See you later.